Section 6 of the National Geographic Magazine, Volume 4. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Marianne. Studies of Muir Glacier by Harry Fielding Reid. Part 4. Measurements of ice flow. Motion of the ice. I had hoped to make an extended series of measurements of the motion at different parts of the glacier, but the pressure of other work and the great extent of the ice forced us to be content with a measure of the motion near the mouth. The reported motion of 70 feet a day was so great that we felt that careful precautions must be taken to avoid all error. We determined not to trust to sightings on pinnacles, but to set out a series of flags whose identity could not be mistaken. The middle part of the glacier is deeply crevassed, and in reaching the proper positions for planting the flags considerable difficulties were met; but, as in all such matters, this only added zest to the undertaking, and we set ourselves to the task of crossing the ice near its end. In this we were unsuccessful, although when setting out the flags we made 5 or 6 attempts, first from one side and then from the other. The furthest points reached from the opposite sides were about 500 yards apart, and although this interval is greater than we wished, still it was not much greater than the average interval between the flags, and so our series was practically continuous. See map of ice front, Plate 15. 2 independent sets of measurements were made, the first on a series of 10 flags from July 21st to 24, the second on a series of 9 flags from August 4 to 8. The first 3 flags on each side were recovered after the first set of observations and replaced, so that observations on them extended from July 21st to August 8, a period of 18 days, with a corresponding increase in accuracy in the determination of their daily rate. 3 or 4 days was about as long as the flags would stand before falling, although they were planted in holes 18 inches deep. The flags marked with 1 dash belonged to the first period, those with 2 dashes to the second; the others were observed during both. No results were obtained from 7 prime as it fell between July 21 and 24. The flags were observed from E and K, which were 5,513 yards apart, about 3¼ miles. Those were the most available points of observation, and although they were not well adapted for determining with high accuracy the actual positions of the flags, still these positions were determined with quite sufficient precision. The direction of the motions could not be determined from our observations, for very small errors of observation produce large errors in this direction. This, however, was unimportant, for the direction is given by the moraines, which was about at right angles to the line E—K. The change in the positions of the flags could be well measured from these stations, as the motion made a large angle with the lines joining the station to the flags. The part of this motion at right angles to E—K was taken as the actual motion. We have thus for the first period, July 21 to 24, 2 independent measures, one from E and one from K, which agree very well. The average is given in the table. For the second period, observations of motion were made from K only. The observations on the side flags from K, which extended from July 21 to August 8, are given in the column headed III, and in the last column are collected what I consider the most reliable results. It will be seen that the motion scarcely observable at the sides increases rapidly toward the center, where it amounts to about 7 feet a day. A consideration of the size of the instruments, their distance from the flags, and the size of the flags themselves shows that there is a possible, though scarcely probable, error of some 2 feet in the determination of the motion of the center flags, and not more than half so much in that of the side flags. Table showing motion of the flags in the ice. Flag. Number 1, color black. Distance in feet from E, 13,622. Distance in feet from K, 4,321. Daily motion of flags in feet. Romanet 1. Daily motion from July 21 to 24. 0.0. Romanet 2. Daily motion from August 4 to 8. 0.7. Romanet 3. Daily motion from July 21 to August 8. 0.0. Romanet 4. Best value of daily motion deduced from Romanet 1, 2, and 3. 0.4. Flag number 2, color red. Distance in feet from E, 12,064. From K, 5,850. Daily motion of flags in feet from July 21st to 24, 3.0. From August 4 to 8, 2.3. From July 21 to August 8, 2.6. Best value of daily motion, 2.6. Flag number 3, color black. Distance in feet from E, 11,155. From K, 6,614. Daily motion of flags in feet from July 21 to 24, 4.4. From August 4 to 8, 4.9. From July 21 to August 8, 5.9. Best value of daily motion deduced from Romanets 1, 2, and 3, 5.9. Flag number 4 double prime, color red. Distance in feet from E, 10,384. From K, 7,438. Daily motion of flags in feet from July 21 to 24, blank. From August 4 to 8, 6.6. From July 21 to August 8, blank. Best value of daily motion deduced from Romanets 1, 2, and 3, 6.6. Flag number 4 prime, color red. Distance in feet from E, 10,207. From K, 7,553. Daily motion of flags in feet from July 21 to 24, 4.8. From August 4 to 8, blank. From July 21 to August 8, blank. Best value of daily motion deduced from Romanets 1, 2, and 3, 4.8. Flag number 5 prime, color black. Distance in feet from E, 8,937. From K, 8,603. Daily motion of flags in feet from July 21 to 24, 6.1. From August 4 to 8, blank. From July 21 to August 8, blank. Best value of daily motion deduced from Romanets 1, 2, and 3, 6.1. Flag number 5 double prime, color black. Distance in feet from E, 8,744. From K, 8,819. Daily motion of flags in feet from July 21 to 24, blank. From August 4 to 8, 7.1. From July 21 to August 8, blank. Best value of daily motion deduced from Romanets 1, 2, and 3, 7.1. Flag number 6 prime, color red. Distance in feet from E, 8,498. From K, 8,921. Daily motion of flags in feet from July 21 to 24, 7.2. From August 4 to 8, blank. From July 21 to August 8, blank. Best value of daily motion deduced from Romanets 1, 2, and 3, 7.2. Flag number 7 double prime, color red. Distance in feet from E, 7,339. From K, 10,515. Daily motion of flags in feet from July 21 to 24, blank. From August 4 to 8, 6.2. From July 21 to August 8, blank. Best value of daily motion deduced from Romanets 1, 2, and 3, 6.2. Flag number 8, color black. Distance in feet from E, 6,378. From K, 11,106. Daily motion of flags in feet from July 21 to 24, 5.7. From August 4 to 8, 6.9. From July 21 to August 8, 6.2. Best value of daily motion deduced from Romanets 1, 2, and 3, 6.2. Flag 9, color red. Distance in feet from E, 5,226. from K, 11,936. Daily motion of flags in feet from July 21 to 24, 4.3. From August 4 to 8, 4.8. From July 21 to August 8, 4.9. Best value of daily motion, deduced from Romanets 1, 2, and 3, 4.9. Flag number 10, color red. Distance in feet from E, 3,652. From K, 13,275. Daily motion of flags in feet from August 21 to 24, 0. From August 4 to 8, blank. From July 21 to August 8, 0.7. Note: this determination was made from E for the period July 21 to August 4. End note. Best value of daily motion deduced from Romanets 1, 2, and 3, 0.7. In addition to the flags, 5 stakes were planted in a line and about equal distances apart on the eastern side of the glacier, as shown in the map. Their movement was determined from August 6 to 29. The table gives the total movement during that time at right angles to the line of the flags, which was the direction of the slope. The direction of the moraine shows that this is approximately the direction of motion. Movement of stakes: A, 0, B, 7 inches, C, 11, D, 3.5, E, 0. This amounts to about 2 inches a day for the middle flag. Conditions holding at the ends of glaciers. Alpine glaciers. It has long been recognized that the comparatively stationary position of the end of a glacier is due to the general equality between the quantity of ice flowing down and the quantity melted. The mean temperature of the valley increases as we descend. If, therefore, the end of the glacier should advance beyond the point where the rate of melting equals the rate of supply, the ice would melt more rapidly and the end would recede. If, on the other hand, the glacier should not reach this point, ice would flow down faster than it would melt, and the end of the glacier would advance. This point is not merely a point of equilibrium, but a point of stable equilibrium. This explanation is sufficient so long as we merely look upon the end of a glacier as a whole. But when we consider each part of the end by itself we are met by difficulties which do not seem so far to have been noticed. As one approaches the end of the glacier the surface of the ice becomes steeper and steeper, and frequently becomes too precipitous to allow one to stand on it. The diagram, Fig. 1, shows the form of the surface cut by a longitudinal section. Now why does the glacier assume this shape? We know that the surface of a drop of water or of a small quantity of honey on a plate will assume some such shape. But this is the result of molecular forces which cannot have any appreciable effect on large bodies like a glacier. The end of a flowing lava stream will have a somewhat similar form, but this is a case of continued flow and not one of equilibrium. These analogies throw no light on the question. If we divide the glacier into layers by a series of surfaces parallel to the direction of flow, the condition that the end shall be stationary requires that the ice supplied by each layer shall be melted at its end. Now the upper layers move more rapidly than the lower ones, therefore their ends must melt more rapidly. A glance at the diagram will show that, on account of the form of the end of the glacier, the ends of the upper layers expose a larger surface than the lower to the air and sun, resulting in their more rapid melting. This, although undoubtedly a part of the explanation, is not the whole of it, for the form of the glacier's end would be one of unstable equilibrium. If anything should cause the surface to become somewhat steeper, the exposed ends of the upper layers would become smaller, and these layers would no longer melt away rapidly as they advance. The surface would continue to grow steeper until the upper part would break off and thus restore the slope. Although glaciers have been observed to advance, I have never heard of it occurring in this manner. A series of measurements of the rate and direction of motion and the rate of melting at the end of some glacier, such as the Gorner or Morterasch in Switzerland, would undoubtedly throw light on this problem. At the end of the valley of Norris Glacier, Taku Inlet, there is a broad expanse of gravel, etc., on which the glacier, after issuing from its gorge, spreads itself like a great fan, thus presenting a large surface to air and sun, so that the melting of the ice is as rapid as the supply. If it were prevented from spreading it would extend much further than it does, and would undoubtedly reach deep water. The Taku Glacier, close by, finds no such support at the opening of its gorge, and therefore discharges into the water as a tidewater glacier. Davidson Glacier, Lynn Canal, has a termination exactly like that of the Norris. The great Malaspina Glacier seems to be merely the united ends of the many large glaciers flowing from the St. Elias Alps, expanded on the great plateau which borders these mountains on the south. Tidewater glaciers. The Muir Glacier is an excellent example of this class. The inlet into which it pours increases in depth from the sides to not less than 720 feet near the middle, but the ice is so thick that even this depth is not sufficient to float it. Here we have an entirely different method of waste. The ice breaks off and floats away in the water as icebergs. What is it that regulates the rate at which the ice breaks off? What is the form of the glacier's end below the water? Above, it is practically vertical. I can only give a partial answer to these questions. Suppose the end of Muir Glacier were vertical from top to bottom. Let us apply what we know of the motion of glaciers to this case and see what would follow. The more rapid motion of the upper part would result in its projection beyond the lower part, and this would become greater and greater until its weight was sufficient to break it off. The extent of the projection before a break would occur depends evidently on the strength of ice. The water supports the ice by its buoyancy, so that the weight tending to cause fracture is slightly less than the weight of that portion of the ice which is above water. The line of a fracture is determined by the position of some crevasse or some irregular melting below the surface. This form seems to be one of stable equilibrium, for if the ice should project too far it would break off, and if it did not project far enough no break would occur until its proper motion had carried it out further. That the ice for several hundred feet below the surface does not in general project further than that above is evident from the fact that I have frequently seen large masses extending to the very top of the ice front shear off and sink vertically into the water, disappear for some seconds, and then rise again almost to their original height before turning over. If there were any projection within 300 feet of the surface, this mass would have struck it and been overturned so that it could not have arisen vertically out of the water. Let us picture to ourselves what takes place at the end of the glacier, noting first that there are three ways in which the ice breaks away. A piece may break off and fall over. This is the usual way, with small pinnacles. B. A piece may shear off and sink into the water. This is the usual way with larger masses. Or again, C. Ice may become detached under water and rise to the surface. The diagrams in Fig. 2 illustrate what I conceive to be successive forms of the ice front. They show how, after a number of pieces break off from above, one large piece will break off from below, but, in all probability, not from near the bottom. The broken lines show where the break occurs. The dotted lines show the form of the front just after the last break. In addition to waste by breakage, there is waste by melting. Above the water surface this is unimportant, for there the quantity of ice floated away is much greater than that melted. But near the bottom of the glacier, where the motion is very slow, the melting is the principal, probably the only, cause of waste, for the ice is in contact with water which is probably not very cold, and is, moreover, salt. That the ice does not melt below water more rapidly than it does in the air is shown by the fact that icebergs roll over, which is due to this alone. It is quite possible that the icebergs, darkened by mud and rock, may not have come from the bottom, but may be merely exposing the side of some old crevasse into which debris from a surface moraine has fallen. The bergs which we saw rise from below the water usually came up after a very heavy fall from above, as though some crack had been started by the shock of the falling ice. Only a few of them were discolored by debris. Most were pure blue ice. Moreover, they did not rise very high out of the water. All this makes me think that they did not originate at any very great depth. Just as a stick thrown obliquely into the water may rise again at an angle, so a berg, on account of its shape, may rise so obliquely as only to reach the surface some distance from the ice front, thus suggesting that the glacier sends out a foot along the bottom of the inlet, from the end of which the ice breaks off, but the considerations I have mentioned make it evident, I think, that this is not the case. A series of observations on the temperature and density of the water of Muir Inlet at different depths and at different distances from the ice would undoubtedly afford information that would enable us to reason very accurately about the form of the ice front below the water. The ice at the bottom of the glacier in contact with its bed moves very slowly, and it is not improbable that the melting where it meets the salt water quite equals the advance. The slope from that point up is determined by the strength of the ice. If the progression of the bottom is greater than the rate of melting, the glacier will advance until it comes to a broader part of the fiord, and thus presents a broader front to the water. If the fiord were of uniform depth and breadth, the ice could only find a position of equilibrium at one end or the other. The effect of the depth of the water in determining the position of the glacier's end is not apparent. As the depth is greater the pressure against the ice is greater, but at the same time the water produces a greater upward pressure on the ice, diminishing its pressure against its bed and thus reducing the friction. Although these effects cannot balance at all depths, I am unable to indicate which one is in general the stronger. If a glacier reaches water which is so deep that it does not touch the bottom, and the motion of the ice is more rapid at the bottom than the melting, then its end will be forced further and further into and deeper under the water, following the slope of the bed until the buoyancy of the water is sufficient to break it off. The place where the fracture will occur and the size of the iceberg formed are problems of mechanics. Glacial erosion. The general scratching and smoothing of rock by glaciers is familiar to all. Another method of erosion, not so generally recognized, was observed here. The spur of Tree Mountain, which I have already mentioned and on which we camped one night, is a compact slate. Parts of it were smoothed and scratched, other parts bore a confusion of mixed rocks, the rock of the spur largely predominating. In still other places the bed rock shows where angular pieces have been broken out, leaving holes which in some cases contained water. Near the summit of Nanatuck H is a rock basin lake, which must have been formed in the same way. It is about 40 feet long and 20 feet wide. Its sides are much scratched. On one side the rock rises vertically 8 or 10 feet above the water. The rock which formerly filled this hole, separated probably by joints from rock beneath, must have been torn out by the ice in its passage over the spot, not necessarily as a whole, but possibly by pieces. The rocks thus torn out are in part pushed by the glacier to its end, in part rubbed and ground into fine mud and carried off by the subglacial streams. This method of glacial erosion seems to me much more efficient in digging valleys than the simple scratching and smoothing that is so much more noticeable in valleys formerly occupied by glaciers. Probably the best method available for determining the rate of erosion is to calculate the amount of sediment carried off by subglacial streams, as Professor Wright did. Repeating his calculation with more accurate data at our disposal, we find that an average of about 3/4 of an inch is eroded annually from the bed of Muir Glacier. The erosion, of course, cannot be uniform, but must vary much, both the nature of the rock and the thickness and rate of motion of the ice. Near the mouth of the glacier all of these conditions cooperate to increase the action, for the rock is slate, the motion more rapid, and the thickness of the ice probably greater than elsewhere. It does not seem excessive to consider the erosion here 5 or 10 times as great as the average. The sudden fall between G and H probably marks the line between the harder crystalline rock above and the softer slate below, and is probably due to different rates of erosion of these rocks. Meteorological notes. The prevalent wind on the Alaskan coast is from the southwest, but the glacier, by cooling the air in contact with it, produces a cold wind which slides down its slope. Thus a northeasterly wind blew continuously at our camp except occasionally when a strong southerly gale overcame it. On the western tributary the wind was from the west, and in Main Valley from the northwest. In fact, everywhere it flowed down the slope of the glacier. Its influence on the temperature was very marked. The mean temperature during July and August was 45.1 degrees Fahrenheit, about 10 degrees lower than that at Juneau during the same period, although the latter place is only about 35 miles further southward. At no time during our stay, however, was a freezing temperature reached. This cold wind did not usually extend very high. Frequently mist could be seen moving northward not 1,000 feet above our camp, where the flag was streaming towards the south. The temperature was higher on elevations than lower down. At 1 prime, 3,000 feet, the thermometer was once observed 6.7 degrees Celsius, 12 degrees Fahrenheit, higher than at camp. Also at the same time, on the top of Tree Mountain, 2,700, the temperature was 4.3 degrees Celsius (7.7 degree Fahrenheit) higher than at camp. The increase of temperature with altitude causes an unusually rapid decrease of density in the atmosphere, with a corresponding increase in refraction, thus producing the mirage which is so common here. It is noticeable only when both the observer and the object are in the cold layer. A ray of light may reach the observer after following a horizontal path, or after rising slightly and then being refracted down again. The result is to make the object appear stretched out and to give it increased height. We often saw islands with apparently vertical sides. The icebergs in Glacier Bay were magnified vertically, so as to look like the ice front of another glacier. The pinnacles of Muir Glacier sometimes look like minarets. These appearances have given rise, by a considerable stretch of the imagination, to the so-called Silent City or Phantom City figuring in some books which describe this region. This mirage is just the opposite to that seen in hot deserts. There the rays are bent up, making the image look as if it were reflected from the surface of water. Here the rays are bent down, yet the bending is not sufficient to entirely separate the image from the object, but only makes the latter appear distended, as though it were made of rubber and had been stretched upward. We had rather less rain than we expected. About 1 day in 3 was rainy during July and August. September was much wetter. There were no thunderstorms, and usually the rain was in small drops. In August, aurorae were frequently seen, so frequently that I think they must have occurred every night, possibly all the time, although, of course, daylight would have masked them. Earlier in the summer the twilight which lasted all night would also have drowned them if they occurred. The survey. A base line was measured off with a steel tape from A to B on the plateau on the western side of the inlet. Here we found fairly even ground. The base was measured twice, first from B to A, then from A to B. The two values obtained were 962.301 and 962.330 meters respectively. The length adopted was 962.32 meters, equals 1,052.8 yards. By means of small transits we then made a network of triangles and fixed the points A, B, D, camp, E, K, L, M, B4, C2. The maps were made entirely with the planetable. This instrument was set up at camp D, E, H, L, N, O, P, R, S, T, and V for the general map. The map of the inlet and the ice front was made from camp D, L, and M. Photographs were made from many points, and these have been of the greatest use in drawing in the general topography. As to the accuracy of the maps, I think that none of the points marked thus (circle with a dot in the middle) are out of their place by 1% of their distance from E. Many are much more accurately fixed. Many points where the rocks and ice were in contact, etc., were of course determined, but with much less accuracy. In order to connect our map with any future survey that may be made in this region, we made 2 cairns of heavy stones, one at D and one at E. D is on the gravels on the eastern side of the inlet, at a height of 107 feet above mean tide. E is on a flat knoll of the ridge descending from Mount Wright at an elevation of 890 feet. The horizontal distance between D and E is 2,735 yards, and the line connecting them runs north 41 degrees 43 minutes east astronomical. The latitude of our camp was determined on several occasions. The average, 58 degrees 49.7 minutes, can hardly be in error by more than a half minute. The longitude was not determined. On first going into camp the chronometer was allowed to run down, and when we left it stopped for some reason unknown. The chronometers of the steamers were not sufficiently accordant among themselves to give reliable results by comparison with our local time. The longitude adopted by reference to the best map of the region in the Coast Survey Office is 136 degrees 5 minutes west, which can hardly be in error by 5 minutes. On platting our map into the general chart of the United States Coast and Geodetic Society, we see that the area we surveyed occupies much of the region between Lynn Canal, Chilkat River, and the upper part of Glacier Bay. The mountains on the eastern part of our map must be visible from Lynn Canal, which is only 10 or 12 miles distant. Davidson Glacier must have tributaries in the mountains which close in Granite Canyon. There is a rumor that the Chilkat Indians were accustomed to make the passage to Glacier bay over the Davidson and Muir glaciers. If this is true there is probably a low divide between some tributary of Davidson and the first northern tributary of Muir. This region, unfortunately, we were unable to see. The scale of the general map is 1/150,000, which is large enough to show the detail we were able to make out, except in the neighborhood of the mouth of the glacier. I have added contour lines at 200 feet intervals. It must be remembered that these pretend to no accuracy, but merely serve to show the general form of the surface as well as I can indicate it by aid of memory and photographs. The altitudes above mean tide which were determined trigonometrically are given in black figures, those determined by barometer or estimated in blue figures. Camp Muir was estimated to be 25 feet above mean tide. From the inlet I have made a separate map on a scale of 1/30,000, which shows well the position of the flags we used for measuring the motion of the glacier and the form and position of the ice front at various times. The contour lines here are only very roughly approximate. The interval between them is 100 feet. The numbers give altitudes, determined trigonometrically, except those on the contour lines, which are estimated. End of section 6.